Hi, in this segment, I want to talk a little bit about the force of friction. And so, in the previous segment, I mentioned that there's kind of two ways we can categorize friction. We can categorize friction as static friction, when two surfaces are not slipping with respect to each other, or kinetic friction, when there is something slipping. And then we're going to add a third one, rolling friction here, which is just the friction that some rolling object experiences. First off, let's talk about static friction. So static friction is what happens when there is no slipping between the surfaces. So here we have this pumpkin. It is sitting on my table, and right now, what forces are acting on it? Well, hopefully you said that there is a normal force up and there is weight down. Is there friction now? There's not, right? Those are the only forces acting on the pumpkin because friction is always parallel to the surface. So friction would either have to be this way or this way. And as we can see, the pumpkin is not accelerating, and therefore the net force in both the y and the x directions are zero. In the y direction, we have normal force up and weight down. Since the pumpkin's not accelerating, the normal force must equal the weight. In the x direction, there's just nothing happening. So there's no friction either. What if I come along and I push on my pumpkin? Now, I am pushing on my pumpkin just a little bit. So I push in this direction, but the pumpkin is not accelerating, right? So there must be a friction force in this direction. If I push a little harder, then friction pushes a little harder, but the pumpkin's still not accelerating, right? So as I push harder, friction must be pushing harder also. In other words, that force of static friction can go all the way from nothing to something small. Now I'm pushing really hard. Something bigger. Something really big. Oh my gosh. And now it's going to start moving. And now we are in the kinetic friction realm. So again, if I take some object and I apply some push to it, and then static friction pushes back. If I push very gently, then static friction pushes back gently as well. Why? Because the object's still not accelerating. Therefore, the net force in the x direction must be zero. If I push a little harder, then static friction pushes back a little bit harder. I push still harder, and now I'm pushing as hard as static friction can. Now I'm pushing so hard that static friction is at its max, and if I push even a little bit harder, then we'll see that the object will start to move. So we can make this graph, and over here we're going to graph the force of friction. And over here we're going to graph the force applied. So in other words, this axis here, our horizontal axis, is like the force of the push. And over here we see this is the force of friction. And what did we see? When I did not push on the friction did not push back, right? And so we start down here at the origin. Zero applied force, zero friction force. The harder I push, the harder friction pushes. And so we get this straight line here with a slope of 1, actually. The harder I push, the harder friction pushes. But you know what? There's a point at which static friction can no longer push back as hard as I am. And at that point, the object will start to slide, and we get kinetic friction, not static friction. And so we label this point right here, is Fs max. That's the very greatest that the static friction force can ever be. Once I'm pushing harder than that, if I continue to push harder, then the object will break loose and it will enter the kinetic realm. This point right here, that is the value of kinetic friction. Okay. The equation we have for static friction is right here. It says that Fs max equals the normal force times this number here. This number here is what we call the coefficient of static friction. That's a Greek letter mu, and so I would say this, mu sub s. So mu sub s is the static friction, the coefficient of static friction. And what it says is how rough a surface is. So it's a unitless number, typically between 0 and 1, although it doesn't have to be between 0 and 1. And it characterizes the interaction between two surfaces. So for example, ice skates on ice would have an incredibly low mu. I don't know, maybe 0.05 or something. A racing tire on asphalt would have a very high mu. Actually, they can even be greater than 1 at this point. When I was in college, they used to teach us that mu can never be greater than 1. But that's old news. Modern racing tires can absolutely have a mu that is greater than 1. Something like socks on a wood floor would have a fairly low mu, but somewhere in between. Maybe 0.15 or something like that, right? Sandpaper on wood would have a very high mu, right? So mu is this number that characterizes how rough the interaction between two surfaces are. Again, typically between 0 and 1. The tires on your car on regular asphalt probably have a mu very close to 1, probably 0.9 or something like that. One other thing to watch out for is that this is an equation for the maximum that static friction ever is, right? To look back at this graph, right, this is an equation for this point right here. The force of static friction can take on any value in here, up to Fs max, anywhere between 0 and Fs max, right? Static friction can take on any one of those values. So we do have to be a little bit careful. When can we use this equation then that I've given? Fs max equals mu times, or normal force times mu sub s. Well, we're going to be looking for these keywords for like before it slips, right? How fast can the car go before it slips? What's the fastest the car can slow down? What's the fastest a car can take a corner, right? If we're talking about those kind of things, fastest, then we're looking for the greatest that the static friction force could ever be. I could ask you problems where I'm going to ask about this range right here. Those tend to be a little trickier because of this this fact that we can't use that equation, but certainly well within the bounds of this class. Okay, so that's static friction. Kinetic friction is kind of similar. In a way, kinetic friction, though, is more straightforward. To bring the pumpkin back, right? If we're in the static realm, right? If I push a little bit, then static friction pushes back a little bit. If I push harder, static friction pushes back harder. That's not quite the same with kinetic friction. If I start this thing moving, then kinetic friction is at some value. And that kinetic friction, it actually doesn't matter if I move the pumpkin quickly, if I push very hard, or if I push just barely enough to keep it moving, right? So kinetic friction is in a way a little bit simpler because it only has one value. It can't take on this whole range of values as I showed you in my chart. So here's a schematic that kind of represents that same thing. Here we see I'm pushing the box slowly. Kinetic friction has some value. And if I'm pushing it at a constant speed, then the force of my push must be exactly equal to that force of kinetic friction in order to have a net force of 0 with an acceleration equal to 0. However, if I push this box fast, so now I'm pushing it very quickly at a constant speed, once again, kinetic friction is the same value, and so my push is actually the same value as well. So again, kinetic friction is in some ways more straightforward because it only takes on one value. And so notice in our equation for the kinetic friction, we don't say F sub k max or anything like that, or less than or equal to. We just say this is what the force of kinetic friction is. Once again, mu sub k is the coefficient of kinetic friction, and once again, it is a unitless number. Mu sub k is always less than mu sub s, and we can see that in this graph that I made, right? That's what this little difference comes from here, right? Mu sub k is always less than mu sub s is. And so this is why if you're driving down the road on a really slippery day in the winter, then as long as you don't start to slip, you're okay, right? As long as you can stay in the as long as you can stay in the static friction realm, you have more friction available to you than if you start to slide. Once you start to slide, the force of friction goes down, and you just keep sliding until you're able to somehow come to a stop. Now you can return to the static friction realm, and maybe you can start going again. Now we can also talk about rolling friction, and rolling friction is the same kind of idea. It's a little bit harder to wrap our brain around because we can just feel static friction, right? We can just feel static friction when we just push like that, right? And we can feel kinetic friction when we let our hands rub, and we can feel our hands get warmer. But rolling friction is just a little bit harder to wrap our brains around, but it's the same kind of idea. Rolling friction is a thing, though. Here's my tennis ball. If I give it a little nudge, what happens to it? It came to a stop. I think my table's pretty level. Why did it come to a stop? Friction. Must be. What kind of friction? Well, it can't be static friction for various reasons. It's not kinetic friction because there's no slippage. Rolling friction? I guess we'll call it rolling friction. Again, rolling friction has a similar equation. It's not confusing like static friction where it can take on different values. And typically the values are much, much less. So in general, we have the situation that mu sub s is the greatest. Mu sub k is less than that. And then mu sub r is the smallest of all. So this is a general relationship that we can just kind of count on. Okay, otherwise it acts very similar. Like kinetic friction, rolling friction does not depend on the speed. Let's do an example. We're going to read it really quickly and just kind of let it flow over us, and then we're going to go back, read it more slowly, and transfer some stuff onto our paper. A sled with a mass of 20 kilograms slides down a slope that is inclined at 20 degrees above the horizontal. The coefficients of kinetic and static friction are mu sub k equals 0.2 and mu sub s equals 0.4. At one instant in time, the sled is moving at 4.5 meters per second. And then we're supposed to find the acceleration at this instant and determine whether it's speeding up or slowing down. Okay. What kind of a problem do we think this is? Well, it's asking for the acceleration. So that means it's either going to be like a big 5 ramp motion problem, or it's going to be a force problem. But let's see. It did give us a velocity, didn't it? But it didn't give us the velocity at a later date. So this could be a later time. So this could be an initial or a final velocity. It didn't give us distance or time. So we have a velocity, but we didn't give, it's not, right? Notice there's no time interval really described in this problem, right? It doesn't, or a distance, right? It doesn't tell how far it went or how long it lasted, right? It's just at one instant in time, what is the acceleration? We just don't have enough information at all to do this as a one-dimensional motion problem. And maybe right now you can't see that. That's fine. Maybe you would see this and think, oh, one-dimensional ramp problem. Well, you would just set it up, write your big 5, find you didn't have enough information, and then you just have to think of a different strategy. So, what kind of a problem is it? Well, it's asking for acceleration. It gave us some information about friction. Dang, I think it's a force problem. Okay, so we're dealing with a force problem. We have a sled with a mass of 20 kilograms. And it slides down a slope that's inclined at 20 degrees above the horizontal. Here's my sled. It tells us that mu sub k equals 0.2 and mu sub s is 0.4. Okay? And at one instant of time, our velocity is 4.5 meters per second. Okay, so here we've got our picture, our sled. We've transferred our information. Next step in a force problem would be to define a coordinate system and draw our free body diagram. Well, this sled is sliding down this slope, which means the acceleration is either going to be in this direction or this direction. And we don't know what. It kind of depends on exactly how strong gravity is compared to that friction, right? So if the sled is slowing down, we'll have acceleration pointing up the hill. And if the sled is speeding up, we'll have acceleration down the hill. So that's going to help us to fit answer part B. But one way or the other, the acceleration is always parallel to the ramp. And so I think this is a great example of a time when we don't want to use a standard coordinate system. Because if we did, we'd have to solve for an acceleration in the x direction, an acceleration in the y direction. It's not that you couldn't do it. It's just that I think the algebra would be significantly trickier. So I think that we should pick a tilted coordinate system. We'll pick a tilted coordinate system. And now, notice, even though we don't know whether the acceleration is in this direction or this direction, it certainly is in the x direction, right? So now for sure our acceleration is in the x direction. We're going to use a tilted coordinate system in order to achieve that. Great. Let's do our free body diagram. Well, what contact forces do we have? We have a normal force. Remember that normal force is always perpendicular to the surface. You know, we've done about 10 problems in a row now where normal force pointed straight up. And that doesn't mean normal force always points straight up. Normal force is always perpendicular to the surface. In fact, that's what normal means. We have weight. Weight is always down. And we have friction. Friction is always parallel to the surface. Friction always resists slipping. And therefore, if the sled is sliding down, there's my force of friction. Now, is it static or is it kinetic? Well, it says it's moving, so it must be kinetic friction. There we go. There is my free body diagram. Now, which vectors are in two dimensions? Any vectors that are in two dimensions, we need to break down into components, as I mentioned in the solving force problems lecture. So, what do we have here? I see force of the kinetic friction. That is entirely in the negative x direction. Normal force, entirely in the positive y direction. W is the only force that I have to break down. Now, it's a little bit tricky. I find that students have a little bit of a hard time often when it comes to breaking down a vector into components when those components are not vertical and horizontal. Here we have a tilted coordinate system. It does make it a little bit tricky. You know, maybe in this case we should impose our x and y onto our free body diagram to kind of help us understand, right? So those dashed lines represent my x and my y. And so now I can see how I would write my coordinates here, right? We would have w sub y there, and there's w sub x. Now be careful. I'm going to draw something that's wrong really quick, right? A lot of times I see students not do this, but rather they do this. So again, don't do what I'm about to do. This is a good bad example. A lot of times I see students do this. They get their y component right, but then they bring it all the way to here, and they bring it over there. How can I tell that that is definitely wrong? This is wrong again, right? So how can I tell? Well, shouldn't it always be a right angle between x and y? Right? X and y there are not perpendicular. They need to be. If they're not, that's a poorly chosen coordinate system. Also, wx needs to be parallel to my x-axis. It isn't, right? So the right angle always goes between the x and the y components. So we'll fix this up so it's correct again. Again, my right angle always between my x and my y components. And now we've got this angle. Which angle is theta? Right? We've got our right triangle. So my theta could either be here or it could be here, right? Which of those is my 20 degrees? Well, from my drawing, it looks like it's probably this one. And indeed it is. So this is a little trick for you, okay? This is a little trick. If you dash, dash, dash your normal force back, okay? So the normal force points in this direction. If we imagine extending the normal force back, then the angle of inclination of our ramp will always be the same as the angle in between that dash, dash, dash extension of the normal force out and the weight, okay? So let me say that one more time. If we take my normal force and I extend it back, then the angle between that extended back normal force and the weight will always match the angle of inclination of my ramp. Now be careful, that means I have to give you this angle, right? In a different problem, I might give you this angle, and those wouldn't match, right? So it's this angle right here that always matches the angle that exists between the stretching out of normal force backwards and the weight. Okay, so that's our 20 degrees right there. Now we can see that W sub y equals W times what? Cosine of 20 degrees. And we can see that W sub x equals W sine of 20 degrees. Great. I have drawn my free body diagram. I've defined my coordinate system. I've found the components of any vectors that are through 2 dimensions and not just one in my coordinate system that I have defined. Now I'm ready to do the sum of the forces in the x direction and the sum of the forces in the y direction. Since the action here is in the x direction, I'll start there. Maybe that'll be enough and I won't have to do the y, but we'll just see. So the sum of the forces in the x direction then equals mass times acceleration. And notice this is where we get to reap the benefits of having tilted my coordinate system. I don't have to call this a sub x or anything like that. I just call it a. I don't have to include cosine theta or anything like that. It's just a. Great. Now, remember that Newton's second law, it's a recipe, right? Newton's second law, it's different from some other equations. It's not one of these equations where we just, look for the equation that has the thing we don't know in and we plug it in. No. Newton's second law shows us how to create the equation, right? Newton's second law is a recipe as opposed to just some equation you plug into. So, this recipe says take all the forces in the x direction and add them up. Well, in the x direction, looking at my picture, I have 2 forces. I have the force of kinetic friction in the negative direction, and I have the x component of the weight. The x component of the weight is W sine 20 degrees. I'm looking for the acceleration, aren't I? Do I know the weight? Well, I know the mass, so I could find the weight, certainly. But do I know the kinetic force of friction? I don't. Now, I do have an equation that I could plug in, right? Don't we know that the force of kinetic friction is equal to mu sub k times n? We do know that, so I could plug that in. Let's go ahead and do that. W is mg, I'll plug that in also. Okay, now, how many unknowns? I don't know A, and I also don't know N. 2 unknowns, 1 equation. I cannot get a number, can I? Well, luckily, I'm not done with my problem-solving process, right? Luckily, I have not yet done the sum of the forces in the y direction. So let's do that. Now, in the y direction, it's not accelerating, right? The sled is never, ever going to jump off of this ramp. So in the y direction, there's no acceleration. And so what do we have in the y direction? Well, we have a positive n. Again, we're just going to follow the recipe. And we have negative w sub y, w cosine 20. Aha! Now we're making progress, aren't we? How many unknowns over here? Only 1. So we can solve this for n. Again, I'll plug in mg. I could run my calculator and get a number. I prefer to do my algebra first and run my calculator at the end. So I could get a number for the normal force here, but I'm going to wait until the end because I like to run my calculator only once. Every time you run your calculator, you're making a chance to make a mistake. And not only that, if you do make a mistake running your calculator, and I see students do it all the time, and you've done it all the time too, if you do make a mistake running your calculator, you can't check your work with your eyeballs, right? If I make a mistake here, I can just check my work with my eyeballs, right? But if you're running your calculator for every step of algebra, then how do you check your algebra when you made a mistake? And you will make mistakes. You've just got to get out your calculator and run it all again. It's a huge pain, right? So by doing your algebra with letters, you're just setting yourself up to be able to fix those mistakes real quickly. All right, so I'm going to plug in my normal force over here. Now we have minus mu sub k times my normal force. I can write this a little nicer, sorry. Times my normal force. And then plus and let's go ahead and separate that out. Okay, and so now we're ready to just solve this for my acceleration. So all we do is actually, you know what, we kind of already have. Notice there's an m in every single term, isn't there? So my m's cancel, and I do have my equation for the acceleration, don't I? My acceleration then becomes, and again, we can factor out a g. I'm going to rearrange it here just a little bit so it's tidier. And I'm just about out of room here. G is positive 9.8 meters per second squared. Remember, G is always positive 9.8 meters per second squared. A lot of times students get tripped up thinking G is negative 9.8 meters per second squared. But it's not. I already accounted for the direction of the weight right here when I said it was down, right? We already dealt with the direction over here. We don't want to undo that hard work that we've done by including another negative sign here. Okay? So we plug in our numbers here. G is positive 9.8 meters per second squared. Of course, mu sub k, we've got right up there, is 0.2. And so we run our calculator, and we get 1.5 meters per second squared. Okay, let's assess that answer. Does it make sense? I think so. That's a good number. What are we looking for there? Well, if I just dropped this sled, its acceleration would be 9.8 meters per second squared in that direction. So we certainly shouldn't get anything bigger than g, probably. 1.5 meters per second squared, that's a totally reasonable value. Now we can look at this and we can say, okay, is my sled speeding up or slowing down? Well, there's the acceleration. And again, this is where defining our coordinate system and keeping track of our signs becomes important. Notice that I have defined positive x as down the hill. I got a positive acceleration. That means my acceleration is in this direction, and it means that my sled is speeding up. So I'm running out of room here. We'll write it right here. Speeding up. Again, recall our rules. If velocity and acceleration are in the same direction, the object is speeding up. If velocity and acceleration are in opposite directions, the object is slowing down. So, I did this example in the friction section, but really it's another example of using Newton's second law to solve force problems. And so, really, it's another good example of how we just go through those steps, right? Define your coordinates, draw a free body diagram, apply Newton's second law on the x. Oh, we weren't quite done. We still had two unknowns. Went to the y, got our other equation. Another point that I'd like to make here is that notice that in this case the normal force is mg cosine 20. Right? And so we've done a lot of problems where the normal force and the weight were equal. They aren't always, right? If I'm just holding this right here, then the normal force and the weight are absolutely equal. Right? But if I accelerate the ball upwards, then the normal force is greater than the weight. If I'm letting it accelerate in the negative direction, then the weight is bigger than the normal force. Also, if I put it on an incline, the weight will not be equal to the normal force. So the weight is often equal to the normal force, but not always. And how can we be sure? Apply Newton's second.